this example is actually one of the homework problems, but I thought I would do it in case anyone is having trouble with this problem. So let's read the problem first. So that's always the first thing you want to do is read carefully and draw a diagram. So there is a street light that is mounted at the top of a pole, 15-foot pole, and a man is walking away from the pole, and he's 6 feet tall. So I'm just going to draw a little sketch of what that might look like. Here's the street light. And here is the ground. And here is the man who is walking away from the pole. Okay. Then it says, how fast is the tip of his shadow moving when he is 40 feet from the pole? Okay, so let me draw what where the tip of the shadow is. So the light is shining down, it hits the man, and he's going to cast a shadow. So this is what we would call the tip of his shadow. His shadow is right here, okay, caused by this light, and the shadow is here, and here's the tip of the shadow. Now that shadow, because the man is walking along, that shadow is going to move. So let's say the man walked in a few more feet and he was over here and he was just walking along, then the shadow would actually move along in the tip of the shadow would be here. And then if he moved further, the tip of the shadow would keep moving out here as the man walks out. So the tip is moving. It has like a velocity, right? So let's go back a little again. So the man is walking at a speed of 5 feet per second. So this is the rate of change or the derivative of this distance right here. So this quantity, this is the rate of change of that quantity. So I'm going to give this quantity a name. I'm just going to call it x of t, and that's the distance the man traveled at time t. Now the tip of the shadow, much like the man, is also moving, right? And so the rate of change of the tip, well, that's the rate of change of this quantity, this distance, the distance the tip has traveled. And this distance here, the larger distance, I'm going to call y of t, okay? And we're asked how fast the tip of the shadow is moving when he is 40 feet from the pole. So we're being asked, what is dy dt, okay, when the man is 40 feet from the pole. So the second step I always said is we need to write down the changing quantities, some variables. Okay, and as we discussed, we're going to let x of t be equal to the distance the man has walked at time t. And we're going to let y of t be equal to the distance the tip of the shadow traveled at time t. So in this question, the third thing we want to do is we want to think about, okay, well, what rates were given and which rates are unknown, are we being asked for? So going back to the question, we were told that he was walking with a speed of 5 feet per second. So this is clearly a rate. We have the quotient here. And that, using our notation, that would actually be equal to dx dt. That's the rate of change of the man. So that is 5. And then we are asked how fast is the tip of the shadow moving when he's 40 feet from the pole. So we are asked for dy dt. when x of t is equal to 40. So remember, in related rates problems, the key to the problem is that we need to find a relationship between our quantities. Okay, and once we find the relationship between the quantities, we can take the derivative and we can find the relationship between the rates, the relationship between the derivatives, and that's why these are called related rates problems. So in our fourth step, if you recall, we have to find the relationship between our quantities. And in this case, that would be x and y. So what I see here is I see triangles, and I actually see similar triangles because I see we've got this small triangle here, and similar to this larger triangle, right? Because they're both right triangles, and then they share this angle, which means that these angles have to be the same. So these are similar triangles, and so what I can, the relationship I can see is that the ratio between these two sides, which is 6 over 15, so that's the small side over the large side, that actually should be the same as the ratio of this side, this small side, to this large side. Okay, and so so let's do the large side. So this large side is y of t. Okay, and the smaller side is given by, this is actually y minus x, right? So using similar triangles, I can see that this relationship holds. Okay, so remember, this is the ratio between the small side and the larger side opposite this angle. And that ratio, which is 6 over 15, should be equal to the small side here, which is y minus x, divided by the length of the longer side, which is just y. So we're using similar triangles there. So that actually gives me the relationship that I need. And if I go over here, I'm just going to rewrite that a little more nicely by cross multiplying. So I have 15 times y minus x is equal to, let's see, 6y. So we have 15y minus 15x is equal to 6y, or 15x is equal to 9y, right? And so in this case, I'm just going to solve for y, since we're looking for y prime, and that's 15/9 x, or 5/3 x. Okay? So that is my relationship in a nice simplified form. So remember that the very next step is we have to differentiate both sides of this equation with respect to time. So once again, remember, we are not differentiating with respect to x or y. We're differentiating with respect to t. So this ends up being y prime is equal to 5/3 x prime, and that's all. Okay, so you can see that these derivatives actually have a simple relationship. They're proportional to each other. So y prime is always just equal to 5/3 of x prime. Okay. So now the final step is we just want to solve. And we have that y prime is equal to 5/3 times x prime, which was given as 5 feet per second. So 25/3 feet per second is our final answer. When the man is 40 feet from the pole, the tip of the shadow is moving at 25/3 feet per second. So this is our final answer, and you might be wondering, why didn't we ever have to plug in 40? Well, the idea is that we found that the derivative, the speed with which the tip of the shadow is moving, is just a constant number. It's just proportional to how fast the man is moving. It doesn't really matter how far the man is from the pole.